Welcome to this lecture on advanced manufacturing processes. I am Apurva Kumar Sharma from the Department of Mechanical and Industrial Engineering of IIT Roorkee. Dear students, in this session we will discuss about the evaporative pattern casting process, also known as EPC process. This evaporative pattern casting is one of the modern and hybrid casting processes which aims to minimize the production cost and is capable of producing intricate shapes with less efforts in pattern making. Let us see the details of making an evaporative pattern casting, its uses, advantages and disadvantages. The evaporative pattern casting process is also known by other names such as full mold casting process and lost foam casting process. It makes use of patterns made from evaporative materials like foam. The pattern material gets evaporated due to the heat of molten metal as it gets filled. The foam patterns were first patented by H.F. Schroer for metal castings way back in the year 1958. Earlier, expanded polystyrene, also known as EPS, blocks were used for machining the patterns. Bonded sand was used for support while pouring. The process is called as full mold process, wherein the pattern is machined from an EPS block. The process is primarily used to make large one-off castings. In the year 1964, M.C. Fleming used unbonded sand and the process started getting recognized as lost foam casting process, also known as LFC process. In the LFC, the foam pattern is molded from polystyrene beads. In full mold process, on the other hand, bonded sand is used. In the LFC process, the bonded sand is replaced by unbonded sand. The evaporative pattern casting process is a binderless process, wherein no physical bonding is required to bind the sand particles. Foam casting techniques have been known by a variety of generic and proprietary names such as lost foam casting, evaporative pattern casting, cavityless casting, full mold casting and evaporative foam casting. In foam castings, evaporative polystyrene is used to prepare the complete pattern including the gauge and risers. The pattern is further embedded in a no bake type sand. The molten metal is poured through the sprue while the pattern is still inside the mold. The heat of the molten metal is sufficient enough to gasify the pattern and the pattern progressively gets displaced by it. Using unbonded sand and expandable polystyrene pattern, the EPC process is a very economical method in producing complex and close tolerance castings. The expandable polystyrene can be molded into numerous complex and rigid shapes, and it is basically a thermoplastic material. In the EPC process, expandable polystyrene patterns are attached to an expandable polystyrene getting system. A refractory coating is applied to the entire assembly. Once the coating gets dried, the entire foam pattern assembly is kept on loose dry sand in a vented flask. The flask is then vibrated and additional sand is added to it until the pattern assembly gets completely embedded in sand. Subsequently, molten metal is poured into the sprue, which further vaporizes the foam polystyrene as soon as it enters inside. The entered metal solidifies and reproduces the size and shape of the used pattern perfectly to get the desired casting. In this process, the pattern used refers to an expandable polystyrene or foamed polystyrene part, which gets vaporized by the molten metal. Therefore, for every casting process, a new pattern is required to be made, which eventually gets evaporated. Now, let us see the advantages of the evaporative pattern casting process. In the evaporative pattern casting process, no cores are required, making it the most advantageous process. No requirement for binders or other additives, as it is a binderless process. Complete sand reclamation is possible using very simple and inexpensive techniques. In this process, sand shakeout is easy, as the sand is unbonded. Since the pattern used in EPC process is one piece, hence no parting lines are required. Since cores are eliminated, no core prints are required. Further, due to this, there is no mismatch and problems due to the core shifts are also reduced. This reduces the casting defects considerably. Improved casting quality is achieved in this process. Close tolerances are possible. The EPC is an environmentally favorable process. The EPC being a binderless process, efforts on cleaning the molded sand are virtually nil. The EPC process is viewed as a value added process rather than a substitute for sand casting. The EPC is cheaper and much simpler than the investment casting process, as the foam is more readily available and cheaper as compared to wax. The EPC process starts with burning of the foam from the edges and has a natural directional solidification phenomena, thereby not requiring risers. In directional solidification, the solidification starts from the edges of the innermost sections and ends towards the topmost portion. Now, let us also see the disadvantages or limitations of the evaporative pattern casting process. Since every casting requires a new pattern, it increases the cost. The initial cost for die making is also high. In low production items, the cost further increases. There is a limitation on the minimum section thickness of the pattern. Due to lower strengths of the patterns, they can get easily damaged or distorted. Quality of the casting fully depends upon the quality of the pattern. During pouring, as the sand is unbonded due to the difference in the evaporation rates of the material and flow rate of the molten metal, some of the sand may fall down in the cavities generated, thereby leading to a defective casting. Now, let us also see the applications of the evaporative pattern casting process. This process is used for making automotive components like cylinder heads, engine blocks, inlet manifolds, heat exchanger, crankshaft, etc. It is also used for parts fabrication in marine, aerospace and construction industries. Now, let us see the evaporative pattern casting process. The process of evaporative pattern casting starts with the pre-expansion of polystyrene beads. Once these pre-expanded beads get stabilized, pattern sections are formed by blowing them into a mold. A cycle of steam is used to fully expand and make the beads fuse in the mold itself. Clusters are made through assembly of the pattern sections using glue. The gating systems are also similarly glued and attached. A ceramic coating is used to cover the foam cluster. The coating acts as a barrier, preventing the penetration and sand erosion during pouring. Once the coating gets dried, the cluster is placed in a flask along with backing of the bonded sand. Any suitable sand can be used as long as it resists the temperature of the molten metal being poured. Silica sand, zircon sand, olivine sand and chromites are commonly used molding sands. The EPC process has high degree of sand reclamation. Hence, one can use zircon or chromite sands, which are otherwise considered expensive. The strength of the mold can be determined through the frictional resistance between the sand grains. Although higher bulk density is provided by the rounded grains, the mold strength with angular grains is much higher. In order to ensure uniform and proper compaction, a vibrating table is used for the mold compaction. After completing this process, the cluster is packed in a flask and the mold is set ready for getting poured. A schematic sketch of the EPC process is shown in the figure 1. This is the pattern. The pattern is coated and then finally, the pouring is done and the product is obtained. The patterns used in the EPC process are made of expandable polystyrene. A typical pattern is shown in the figure 2. Pattern fabrication starts with the pre-expansion of polystyrene beads. They are blown into the die cavity to form pattern sections. This is a typical polystyrene pattern. When the beads are in the die, a steam cycle causes them to fully expand and fuse together, forming the pattern as shown here. For the fabrication of steeped pattern, die and sprue, a cavity as per the pattern dimensions is prepared. Aluminum is commonly used as the die material. The complete die is fabricated in 2 parts called as male and female. There are 3 inlet pipes 1, 2 and 3 and 1 outlet pipe 4 are attached with male and female parts as shown in this figure. These are inlets, this is the outlet. The function of all 3 inlet pipes was same in male and female parts. The 2 outermost pipes number 1 and 3 were used to supply water as a cooling agent in the die. The middle pipe, which is pipe number 2, was used to supply the steam into the cavity through pinholes to soften and expand the beads. Pipe 4 was used to draw water and steam from the die. Polystyrene beads were fed into the die cavity through a pipe which is connected at the top of the male part. At the four corners of the die, T slots are fabricated to hold both male and female parts of the die in the press. Pattern density and bead size. Density and bead size play important role in evaporative pattern casting process. In order to minimize the amount of gases evolved during evaporation of the pattern, patterns with low density are generally used. The low density patterns ensure that the gases escape out through the coatings, sand, and vent into the atmosphere. Gas formation is a function of the metal pouring temperature and pattern density. If the gas forms faster than it can vent, a defective casting will be formed. If the pattern density is increased, then at a constant pouring temperature, more gas is formed. If the pattern density is held constant and the pouring temperature is increased, more gas will be formed as the polystyrene molecules break into many more basic molecules. The gases formed should pass through the coating on the pattern surface. The pattern density generally varies between 1 and 1.5 PCF, which further depends on the geometry and metal that is being poured. Small beads are required for obtaining relatively non-beady smooth surfaces on the molded patterns. Requirements of refractory coating. The coatings are an inherent part of the casting process and also provide a very good quality surface to the casting. Some specific demands as mentioned below are desired for the refractory coatings in the application of the EPC process. Highly permeable coating is preferred for rougher sand, while medium and low permeable coating is preferred for finer sand. Quick drying is preferred. Coating should get easily stuck to the pattern and there should be provision of controlling and adjusting coating layer thickness. Appropriate strength, resistance to abrasion, resistance to cracks during storage, resistance to bending and deformation during mold making are required. Thicker refractory coating layers are desired in cases where rough sands are used for molding at high temperatures. Coating material. The refractory coating materials play an intimate role in the EPC process. Its function is to provide a refractory protection and seal any penetration of metals. The coating materials should provide smooth surfaces and act as a membrane between the polystyrene pattern and the unbounded sand mass. The unbounded sand mass should be firmly held in place till the polystyrene foam pattern gets decomposed under the effect of the entering molten metal stream. This is achieved by allowing the permeability of the refractory coating to restrict the free flow of decomposition gases and liquids through the coating into the unbounded sand mass. This causes a back pressure against the entering molten metal stream, resulting in a pressure force that holds the unbounded sand in place. The control of escaping gases through the sand mass is done through appropriate selection of the coating material and its permeability characteristics. The coatings are engineered to obtain a variety of properties imperative to the casting process, such as thermal insulation, abrasion resistance and liquid absorption. There are several types of refractory coatings available to be used on evaporative pattern. Some of the coating materials are zircon sand, kaolin, talc, etc. The coating generally recommended in case of cast iron is iron powder, as it prevents the metal penetration. The sillimanite, quartz and aluminum silicate can be used as filler materials to make the coatings cost effective. Now, let us look into the process variables involved in the evaporative pattern casting process. The process variables have a major effect on the quality of evaporative pattern casting process, mold and castings. An Ishikawa cause and effect diagram is shown in the figure 4. Here the major parameters involves the metals and alloys, the vibration, the sand used, the pattern and the coating. The parameters involved in these affect ultimately the casting to be obtained as the product. The EPC process variables can be grouped in the following categories. Number 1, variables based on molding sand used. These are type of sand, shape of the sand grains, grain size and size distribution. Number 2, variables based on pattern. They are density and size of pattern beads. Number 3, variables based on pattern coating. The variables are slurry material, base, filler and additives, and coating thickness. The fourth category of variables are based on the vibration system. The variables are amplitude of vibration, time of vibration, and frequency of vibration. The fifth category of variables are based on pouring. The variables are pouring time and pouring temperature. These are some of the product produced through evaporative pattern casting process. The products obtained from evaporative pattern casting need to be subjected to various tests to ensure its soundness. Few of them are discussed in this session, which are very commonly used. The most widely used technique for measuring the effect of temperature on the samples are thermogravimetry, also called TZ test, then derivative thermogravimetry, also called DTZ test, and differential thermal analysis or DTA test. Then another very popular and very widely used technique is the X-ray diffraction analysis. This is quite old process, but quite comprehensive and quite popular process. This is used to analyze the different phases present in a specimen. X-ray diffraction also gives information about the elements present and its composition. As we know, different materials diffracts the light incident on it, or we can say different electromagnetic radiation incident on it depending on the structure. Therefore, this can be explained like this. If this is the surface and if X-rays are falling on it, this is say X-rays, then this refracted X-rays inside this material. So, this is the material, this is test material. This will be depending on the crystal structure of this material, and therefore, by measuring the angle of deflection, what is this angle, we can find out what is the material in this, because this can be correlated to its characteristic. That means, this diffraction will be characteristic of the material or the crystal structure through which this X-ray, incident X-ray is passing through, and therefore, we can get a signal like this. So, here, so this is 2 theta and this is called intensity. Now, these different peaks, this peaks represents that one element, some element say E1 is present, and that can be confirmed by subsequent detection of 5 peaks, 5 such peaks in this spectra. This intensity is plotted as a function of 2 theta as we have indicated, and by knowing this 2 theta we can identify which element it is, because this 2 theta for different materials, say aluminum for different phases, this 2 theta is fixed. Similarly, for copper different phases, this value is fixed. Now, by correlating these values, if we obtain these values here, then by identifying the peak corresponding to that particular 2 theta value, one can identify the element present in that material. So, this is a very important technique and widely used technique, very low cost technique, and of course, this is a non-destructive testing technique which is very widely used even today in the crystallographic labs. Of course, for subjecting this particular test to a material, the material needs to be crystalline in nature. Amorphous materials like glass etc., cannot be characterized by using this method. Other testing techniques used are scanning electron microscopy, field emission scanning electron microscopy. These techniques help us to study the micro details for greater understanding of the features. The field emission scanning electron microscopy can be used to obtain an information about the constituting elements as well, while scanning electron microscopy gives the microstructure as a whole, which helps us to identify the phases, to identify the microstructure how it is, or to identify whether there is any crack, micro cracks, or whether there is any porosity or any other defects at all. In many cases, microstructure changes with the temperature, or in other words, since the casting is a thermal process and the cast product is nothing but a solidified molten material, therefore, we can say the solidification leaves some footprint of the material to be examined later. Now, using these devices like scanning electron microscope or field emission scanning electron microscope, we can study what are the footprints during the solidification process. Now, as per the heating rate or the cooling rate, here in case of casting it will be cooling rate, the material microstructure, the structure of the material will be changed, and that can be identified using scanning electron microscopes. For example, while producing aluminum alloy casting through the evaporative pattern casting process, some typical observations could be reactions such as dehydration, decomposition, oxidation, or such chemical actions have considerable influence on the coatings, and these can be identified by easily by using scanning electron microscopes. All the reactions are of exothermic type, wherein heat is liberated. This can be confirmed through thermal testing like DTA or differential thermal analysis. Due to the presence of moisture, some degradation is accounted for till a certain temperature range. This can be seen through DTG technique or derivative thermogravimetric analysis technique. Now, let us see the effect of refractory coating on the produced evaporative pattern casting. After dipping the refractory polystyrene in a slurry, coatings in the range of 0.1 to 0.2 millimeter are generally obtained. These coated patterns are dried and compacted after placing them in the molds, which are filled with unbounded silica sands. When an aluminum alloy is poured into it, it results in a sound casting wherein there is no penetration or defects like coal soot. As we know, coal soot is a big problem associated with castings. This is considered to be a defect in casting, and this can be identified with this. The same high finish as on the polystyrene pattern is obtained on the generated casting through evaporative pattern casting. The removal of coating does not take much effort, and it is also possible very quickly. Further, it is seen that particles of different grain size contribute to uniform continuous coatings on pattern due to better packing between the particles. The applied coatings produce stable compounds of titanium oxide, ferrous oxide or aluminum oxide, which depends on the type of sand used. These compounds lead to high temperature refractoriness. Generally, the quality of final casting obtained is very good in terms of its finish and internal soundness. Now, let us summarize what we have discussed in this session. In the present session, we have discussed about the basic evaporative pattern casting process, the steps involved in making it, then the advantages of the process, disadvantages of the process, and the setup details of this process. This setup basically we have discussed, which is developed in the IIT Roorkee itself, and we have discussed some testing methods and effect of refractory coating on evaporative pattern casting process. We hope the session was informative. Thank you.